Okay, so welcome back, everyone. Today, we will be continuing with our Bayesian modeling of, first of all, the binomial example. So the last time I already showed you like step by step how to open up a new script, an empty script, and then write down all of the required blocks in the Stan language. And I will spend a few more minutes like to recap what we have discussed the last time, and then I will run it, and then we will be able to see, and then also to discuss the results and then how to draw some inference on top of it. So again, what we had as a data analysis example is we were interested in like for a few lectures already. So we were interested in how much of the Earth is covered by water, or in other words, how much water is covering the entire Earth. We can't do experiment with the whole Earth because it's huge. Instead, we were trying to operate or to like handle the small world, which is a globe that is available in the shop. So we throw the globe and then catch it, and then to record what is under our right index finger. It is water or land. So what we did is, like in this hypothetical experiment, we had 9 times of experiment. We throw 9 times and then catched also 9 times. Out of the 9 times of experiment or trials, we observed 6 times of water observation, and then the remaining 3, they are land, of course. Because this is a binary outcome, so binary here means it's either water or land, either 0 or 1, like numerically. This is also the same process if you are doing a coin flipping, or if you are doing one exam, you either get one question answered correctly or incorrectly, or if you imagine there's a sports example, a football penalty shootout, you either score or not, right? So all of these binary outcomes can be modeled by a process called binomial process. And so we like summarize in this line, those are our data, right? The second line, this is our model. And we know the model, the binomial, and this is there is something on top of the known part, the number of experiments, the number of water observation, and then there is the unknown part. The unknown part here is the theta. The theta, what is theta? Theta in our example is the proportion of water covering the land. If that is a coin example, theta then means the probability, if you throw the coin up into the air, the probability of the head or the tail landing face up. And if it is an exam example, theta means correctness, so accuracy, how much you can get the answers correctly. If it is a penalty shootout example, then theta here means also success rate. It's how much, for example, Robert Lewandowski could score a penalty shootout when he's playing for Bayern. So those are the examples and the data, the known part, the unknown part. And as we like repeated the idea multiple times, that what is data modeling? Well, data modeling is trying to find the appropriate likelihood function linking the known to the unknown. The known is the data, the unknown is the proportion of water, like theta, and the linking function, or in particular in this case, the binomial function, okay? Known, unknown, and linking function. And then this translates to the implementation of the Stan language. So what we did the last time is, well, we have the known, we have the unknown, so then we also have the linking function. So this is how you literally write everything down into the program. So the known part, we had water observation, we had a total number of experiments. And one thing to pay extra attention to is the data type. So instead of naming only the variable of the data, we will also have to declare the type of the data. So what are our water observation and our trials? They are the integers, right? They're discrete variables. So then we have like, let me get this down a little bit. So we have integers. Integer is the keyword to specify or to declare discrete variables. And we also want to make sure that everything is correct in the sense that they make numerically sense, because negative number of observation of water or negative total number of trials, they don't make sense at all. So we would like to make sure that this will never happen. So we give the constraint that we will always be sure that they are at least 0 or then positive. Similar idea, we translate the parameter from the model, the likelihood function, to the code, that the parameter water covering the entire Earth, it is a continuous variable. So between 0 and 1, it's either positive 1 means 100% water covering the land, well, Venice maybe in a few years, and then 0, so nothing, water, always land. We have the lower and upper boundaries of the parameter. Then it is a real number. A real number here, it is to construct a continuous variable, okay? So then we have everything ready. Then the last part or last bit is to give the connection. So how to connect the known and unknown, which is in our case, the binomial likelihood function. So what we write it is as simple or as straightforward as it is written in the textbook or Wikipedia. So the water observation is distributed as a binomial distribution or function with a total number of trials, n, capital N, and the proportion of water, theta, okay? And you could easily rephrase this line in other examples. So for example, the number of head observation is distributed as a binomial function with total number of coin tossing and a head proportion probability theta. And some other examples. So your number of correctly answered questions in the exam is distributed as a binomial distribution with the total number of questions in your exam and your general accuracy. So everything is the same in this case, as long as you have the binary outcome. All right, so let me just move into R because we did it from the last time. We had something here. We also had our binomial model. It's a little slow. Just to repeat the last time. So we have our data and we put everything into a list. By a list, nothing, but rather than data frame or anything else, it is because lists, the data list, data type, it is something Stan could recognize and could only recognize. Otherwise, Stan will say, well, I don't know where your data is, so give me a data list instead. So then here, as usual, before we use a package, we have to load it. And then there are some specifications I'll tell you later. And then this is the path of the model. So where we tell Stan our model is saved onto your disk. And this one is we call the MC robots idea or analogy. So 20,000 means the robot will move 20,000 steps. And 4 here means how many MC robot we want to send out to discover the space for us. The more the better usually, but because this method is relatively stable and efficient, 4 is a default number. So we just send out 4 MC robots with the hope that even though they will start from random starting locations, they will always converge, they will always go to the top eventually. And here, this number means this variable warm up or burn in some other literatures. This means how many of the samples, there are 2,000 in total, but how many of the samples will be used to determine some internal optimization. So Stan is a language, it will run for some internal steps to find out to figure out some constructions that we don't have to care about, but it is important for itself. So these internal steps will also consume some of the samples. So maybe if out of 2000, we can use 100 to do these internal steps, and then the remaining 1900, they will do the actual sampling. But maybe you would wonder that what is a good number for these internal steps? Is 100 enough if we have in total 2000? So a good rule of thumb is that we always use half of it. So in total, we have 2000, but the first 1000 will for those internal steps. And then the last 1000 will be for the actual more important sampling for us. And then here, the thinning is something I have to explain a little bit. So imagine this is the starting point of a MCMC robot. It moves here and here and here and here. This is here, then here, 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 yeah, here, 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 something like this, okay? So thinning equals 1 means I take all of the sample of the visits. I use this, I use that, I use that, I use that. But if thinning equals 2 or 3, that means I take not consecutive samples or consecutive visits of the MCMC robots. I take every second or every third. So for instance, if I'm using thinning equals 2, I will take a different color. I guess I will take this sample, skip the second, go to the third, skip the fourth and go to the fifth, and skip the sixth, go to the seventh. Okay, you see what I mean? So every second sample, I will take it. If in another, this is 2, okay? If in another case, I am using thinning of 3, then that means I will always start with the first, yes, of course. And then I will skip the second and third and go to the fourth, and skip the fifth and sixth and go to the seventh. Yeah, so every third sample. And I can also go higher numbers. Thinning equals 10, that means I take only every 10th sample. So the first, 11th, and 21st, and so on and so forth. As you could imagine, if we use a higher number of thinning, we will need eventually more samples because we don't use all of them. We only use a sub-sample of it, right? So now the question is, why we are doing this? Why we don't take every single sample? There is a historical reason. So for previous MCMC sampling methods like Gibbs sampling or some other simpler version of MCMC sampling, the samples here, if you go this thing, if you have a trajectory of visits, the samples, they tend to be correlated. So if I visit here, I am more likely to visit also around this area. So if I'm here, my next sample will be more likely around this area, okay? Well, maybe I'm here, then I'm more likely to visit this area rather than I'm going really away from the original sample. So they tend to be more correlated if you look at the trajectory. If they are correlated, that means the sampling procedure is not efficient because the sampler is not exploring the space efficiently enough. So if you always stuck within a small area, how you can go to like the broader neighborhood, right? This is the question. So to reduce this kind of drawback, let's say if I'm here, I know that I am more likely to be still within this area. So then I don't take the next sample. I take maybe 10 samples away from the current one. And then from here again, I take 10 samples away from the current one. And then you see here, if I am using the spatial correlation is very large, reduced, right? It makes sense, but it just takes much longer time to give a more stable estimation. Well, historical reason. But STAN doesn't work this way. So STAN, as we said earlier, it's more efficient, and we don't even need to keep the thinning. This option is here only for historical reasons, to make some people happy, in the sense that if people are more familiar with other MCMC sampling methods they have used for quite a few years, they might want to look for this option. But if it is not there, they might feel this is not good. This is there only for this reason. But we just keep it to be one. We take every single sample, okay? There is actually another part of the story. So I said, if, let's say, look at this line, if there is the spatial correlation, and if I take every 10th sample, it seems like it will become a new line, right? It will become here and here and here, right? All of the everything in between, I don't care anymore. But do you really solve the spatial correlation problem? It's not. The spatial correlation is always there. You just ignore it. You take something further away. You say, well, I don't care the correlated part. I go somewhere further, and then I might be solved. You are cheating yourself, I would say. So it's helpful, it's useful practically, but it doesn't really solve it. It takes a detour to kind of get rid of it, but it's always there. So what I'm trying to say, this is a little bit out of topic, I think, because we're not even using that. What I'm trying to say is, if you're reading the paper, if the paper is using one of the earlier version of the MCMC, they say they use thinning they increase the thinning from 1 to 10 to reduce the spatial correlation. This is incorrect, because they cannot reduce the spatial correlation. The spatial correlation is always there. Instead, what they did is to just took further samples to take spatially uncorrelated samples, rather than they reduce it. They can't reduce the spatial correlation. Okay, you can feel free to forget what I'm saying in the last 5 minutes, because I guess this is a little bit too much. Good. Any questions up to this point? Okay. So what we can do is we just run everything. And I think I have V2. Yeah, let's change this thing to be theta. This line, as we said, can be ignored. Theta, okay. So after coding, we could always check the grammatical or syntactical correctness of the model. So say there's a button on the top right corner, and I click it. Usually don't have to wait, but now I have to wait. To close a few things, yes. Not helpful. Okay, questions? Chrome. Let's close Chrome. This shouldn't take that long. If you run it on your computer, I think it's usually 1 second. Come on. All right, anyway, let's explain these things a little bit more. So this is the main function call, and then this is the place where we tell Stan where the model file is. Data is data list, number of chains is number of chains. So those are the input arguments of the function, right? The iteration 4,000 samples, here 4 chains. Number of warm up equals half of the entire iterations. Thinning is 1. So we take every single sample consecutively rather than take every second, every third, so on and so forth. And here we will have a random location, random starting point, random starting location of the 4 chains. And seed is like, if you are familiar with the idea of random number generation, if I say I want to generate a random number between 0 and 1, and if I say, well, the first random number is just hypothetical example. The first random number is 0.011. The second is 0.64, something like this, okay? And if I generate 2 other random numbers, it will change because it is a random process. The second time, if I randomly generate 2 numbers between 0 and 1, it will be 2 different numbers. But let's say I really want to reproduce myself. I want to have always exactly the same results every single time. So what can you do? Then now the question is how those random numbers are generated, how this randomness is determined, how random it is, all right? This is the question. So in all of the programming languages, random number generation is never random. This is the first message. Random number generation is never random. It follows a quite complicated pseudo-random scheme, but it's never truly random. But anyway, because it follows a pseudo-random sequence, there has to be a starting point. The starting point is the seed, is just the location, the seed. If you plant a tree, then there will be a seed, right? If you plant a random number, there will be a seed. If the seed is the same, so let's say if I use this seed, for example, all the time, I will always get these 2 numbers to begin with if I randomly generate 2 numbers. Why this is helpful is because, as I mentioned, it is to improve or to enhance reproducibility, because every time you run something, because this is sampling procedure, there are some randomness variations, and you might observe a little bit variation from time to time, but if you don't want it, let's say, then you can use the same seed every single time. This is only to like improve open science, let's say. And those are the input arguments. So then now the checking worked slowly, but worked. We have everything correct. That's good. Other questions? I had the same if you, okay, you have to restart RStudio. I just opened that from fresh, I don't know. Anyway, let's see a little bit more things. So what is this and what is this? This is actually only for checking the time. So let's comment it first. And then let's say I want to randomly generate 100 numbers. And I want to know how long this costs, how long does that take? How long R will spend to generate 100 random numbers? Well, I run the entire thing. You can see here. this is the time. This is the time. So these three lines and these three lines is like the sandwich. They are the toast of the bread. One is the beginning, one is the end. And then in the middle is the one that will cost the time. And here you start, you give a time step. When does that start? And then afterwards, you give another time step when it will finish. And you do the minus, you do the subtraction, and then you will do the time it takes, right? So nothing special, a few more lines, but you just don't have to worry about that. It's only for like helping us understand what is going on. Good. Let's get it back. And I would say let's simply run it. Some error, I think. Oh yeah, the model file is the different. I think I changed it. So binomial globe model, okay. Again. Yeah. It will just run. It will take some time. This time it's expected to take some time, a few minutes, I think. The running part usually is the boring part because you have to wait. It depends on how complex your model is. So for simple models, maybe a few minutes. For complex models, maybe a few hours or days. And you don't want to run your model so that let me put it this way, because let's say your computer is a machine, it has computing power. And if your computer is running models, at the same time, it might be that you cannot work on something else. You can't do some other analysis, you can't write thesis. It could also be that the STEM program will consume all of the computing power of your computer. Even browsing the internet, it just freezes and super slow. It's possible. You don't want it. So how do you deal with that? So for people who are really using this software to do analysis, if they have complex models, they really don't want to run everything on their own computer. Instead, they will rely on something called a computing server, or HPC, which is like high computing cluster. Is HPC. HPC is great in the sense that if you have never seen that, it is like a fridge, not only one but multiple. They are stored in a huge garage, something like that, and then they are computing all of they are doing all of the hard computing work, and they are sending it back to you. So it's like a cloud computing, virtual computing. You are sending the job from your computer to the server, and the server does everything for you, and then give you back the results. And now the question is, good, we can run everything on the server, but where is the server? Do we have it, right? In the Faculty of Psychology, we do have servers, and in the city of Vienna, so the entire Vienna city has a computing cluster. So it's called Vienna supercomputer or something. You could apply for computing hours, and then they will give it to you, and then you can just use the resource they have. I think it is free, but you have to write down an application. For you as a master student, you definitely don't need to do that. You don't have to do it. It's tedious. But at a later stage, if you are doing your PhD or anything, if you really need this computing resource, it's something to consider. All right, I killed this waiting time. All right, good. So it takes some time, right? So here 1.6 minutes. And this is the output. The output is a little bit, let's say, busy to read. Let's try to understand what is going on here. So when it started, here there's only one line. It says, click the fresh button to see the progress. And then all the others are blank, nothing. And then I clicked on the refresh button and everything is full. Okay, we have everything. So what do we have? So here we have 4 MCMC chains. From the setup, I tried to tell Stan that I want all of the 4 MC chains to be run in parallel. So essentially here 4 processes from my computer, they were started, and then there's a IDs for like internal computing thing. You don't have to worry. And then they tell you, okay, all of the 4 chains, they started nearly at the same time, okay, right? So it's like 1 o'clock, 45 minutes, 44 seconds, and 43 seconds, nearly at the same time. And here, from here to here, this is one chunk, the first chain. This is another chunk, the second chain, and third and fourth. And they are just repeating, it's the same. Therefore, I will only explain one, right? Because they are the same. So what do we have? We say, well, the models, the program says sampling from this model, now chain 1. This is to remind yourself what is going on now, what is the model you are running, and what is the chain now. And first 3 lines is only for information. It tells you that this process takes 0 seconds, some other process takes 0 seconds, and then adjust your expectation accordingly. So for simple models, this is super fast. This is nearly 0 seconds. It's never 0, honestly, nearly 0. But for complicated models, this initial step will take maybe 3 minutes. So then if you are running 2,000 samples in total, you could more or less imagine that the entire process will take 3-4 hours, roughly. And then this is the progress of the model. So what is the progress? The progress is basically first visit, second visit, third, fourth, fifth, and then so on and so forth until we have 2,000, right? So this is the progress. We have the first out of 2,000, 200, and 400. There's the progress from 0% to 100%. What else do we see? So we see here in parentheses, we have 2 parts or sections. One is the warm-up, and the other one is sampling. So I said that here the warm-up, we take first half to force them to figure out some internal steps. So those are the first half. And then after the 50%, after warming up part, after the internal thing, we have the actual sampling. So those are the actual samples. We have 1,000 of it, right? So now recall we have here for each chain, we have 1,000 samples for the actual sampling. And we have 4 chains, right? So in total, we have 4,000 valid MC samples for our data analysis. Good. So this is everything. And if you write a paper, you never paste this thing to your paper, right? You don't do that. So what do? You will try to make a nice plot to visualize how does this 4,000 sample look like. If the shape is, well, if that's nice or not, that's the data, however that is. You visualize it, and then to use this visualization as a summary of your results. So first of all, we have 4,000 samples. Simply as what we usually do when you are doing analysis, we want to know, well, what is the mean of the 4,000 samples? What is the variance of the 4,000 samples? What is the 50% median? What is the upper 25 quantile, the lower 25 quantile, right? Those are the questions that you may be interested in. So we can indeed actually find all of the information. Again, if you print it, so this is the outcome variable, right? So we print it, and then we will see again some reminding messages to say this is the inference for this STEM model. This is the same as how we named it. If you see my mouse cursor here, this is how we named it. This is the same name. 4 chains, each with 2,000 iteration, warm up half of it, thinning equals 1, and in total we have 4,000 samples. It's the same as I just did the simple calculation. Important is this line here. We named our parameter to be theta, so then we have the mean of our theta, so we have the standard error of the theta, standard deviation of the theta, the 4,000 samples. The first 2.5% quantile, 25% quantile, 50% quantile, the median, 75% quantile, and then the last and so forth, okay? Good. You know what is going on, more or less. And what are these? These are interesting statistics. So this one means the number of effective samples. effective samples. We have 4,000 total. Now we have 1,339 effective samples. Is this good or is this not good? How do you evaluate? This is something that you would have to worry about if you report it in the paper. So as said, MCMC is in general, like the earlier version of MCMCs, there is this spatial correlation. If you are here, then you are more likely to visit your neighbors rather than going to somewhere further away, right? So if your new location and old location, they are spatially correlated, effectively, they are not two samples. They are maybe 1.1 sample because they overlap. They do not have unique contributions, unique and independent contributions. They are correlated. So equivalently, the two samples there, if they are correlated, they are equivalent to 1 point something, between 1 and 2, right? So that is the meaning roughly of a effective number of samples. So HMC the algorithm of it is efficient enough. So this number is actually already high. If we are using something from earlier versions of the MCMC, maybe GIPS sampling, this number will just be a few hundred, okay? But how do you know? So how do you know this is a good number or not? You actually don't know. I don't know. So relatedly, we could use another thing called statistics, right, to evaluate it for us. So in like t-test, we could rely on the alpha, the p-value to help us determine anything is significant or not, the difference. So here's the same. We could use something called a R hat statistics. So this is a number between 1 and the positive infinitive. If it is 1, then that means everything's good. If it is above 1, then that means something is not so good. But what is not good? Is there a kind of threshold or not? So all of the thresholds, they're arbitrary, right? We can say, well, maybe 1.5 is bad. We can say maybe 1.4 is bad. There is a widely accepted biggest R hat that we could accept to make further inference. This is 1.1. So if you read paper, if you look at the reports of the results, they say the largest R hats in their analysis is 1.1, good, great. If the largest one is 1.2, 1.3, you do have to worry about that. So if you are reviewing a paper, if you're a researcher and then the editor find you because they know that you are able to evaluate STAN results, and then they give you a paper and then you look at the paper, you look at the table of the results, you see somewhere of the R hat is 1.2, you really have to worry about that, okay? Below 1.1, everything's okay. Good. And here you even see the information from STAN package, right? The STAN package to tell you that don't only look at here. Don't only look at here. This is a crude measurement of the effective sample size. R hat is potentially more important. So this is more important. So what does R hat actually measure, right? This is 1 is good, 1.1 is okay, above 1.1 not good, but what does that actually measure? It measures the convergence. So what is the convergence of this question? I can show you later on the graph, but I can try to draw. We have one line, we have one MCMC chain, and because they start from a random location, maybe the second one starts from here, but more or less, eventually, they follow each other. They are able to be mixed, right? There's another one starting from a random location. Yeah. This is good. This means the three lines, the three MCMC chains, they overlap or they mix up. They could be able to find the same parameter space. This is called convergence because they converge to each other. From different locations, they converge. But in another case, let's say, well, there's a naughty guy. It starts from here and it goes here. Really bad example. Well, good example for a bad convergence. This is a convergent chain. Okay, this is a convergent chain. So if you calculate the R hat is like this, the hat of the R. if you calculate R hat, if you calculate the R hat for the 3 chains there, R hat will be 1, I believe, because they converge very well. But if you include the last chain, the purple chain, the 4 chains, the R hat, I don't know, but it will be larger than 1. It will be larger than 1. This is what R hat measures. So essentially, we want all of our MCMC chains to converge to each other, and then they will be able to give us reliable data analysis results. Okay, good. Let me go back to the slides. So here it tells the same thing. This is the same thing we see here. We see here is the number of effective sample size. We see the R hat, and the R hat actually has a reference. So whenever you are reporting the R hat statistics, it's actually called Gell-Mann-Rubin statistics. It's actually from 20 years ago, right? Then you are good to go. How can this happen that they don't convert? Because the parameter space can sometimes tricky to be sampled from. If you have a smooth parameter space, they won't go wild. But if your parameter space is quite tricky itself, then it's possible that the chains, they don't visit the same place. Make sense? And how many chains do you need to be confident in your results? 4 is okay, good to go. 4 is the default. I've seen people use, I mean, so at least 1, right? At least 2. I've seen people who use 2 MCMC chains. I'm quite skeptical, but those papers that are published anyway, it's fine. 3 is the older standard, like before 2015. And after 2015, I think most people, they are using 4 chains. Occasionally, I see 8, 6, 10, but I never seen beyond 20 chains. It's not even efficient. You are using a lot of computing resources, but in the end, you don't really gain too much efficiency. It's just a little bit waste, I think. 4 is good. 4 is good. The default. And what I can tell you is personally, I've never used more than 4 chains. I just use 4. Good. Okay. And so since we have the results, we have the actual results instead of the drawing I had. So here we are able to visualize all of the 4 chains. So what you can see here, we have the chain ID, the 1, 2, 3, 4 different colors. They mix up pretty well. There's no naughty guy, no chain is going super wild. They are more or less visiting the same area of the parameter space. And one interesting observation here is if you look at the x-axis, the starting is not 0, it is 1000. So remember, first half of the chains, they are discarded. It's not for actual sampling, it is for the internal steps. But if, let's say, you, for whatever reason, are indeed interested in the first half, you can always visualize it. So actually, you can see here from the very beginning, you see here, there's a little bit, the purple line is a little bit larger than the others. So in the beginning, it's more noisy, it's much noisy. And if you look at the second half, the level of the overlap is better than the first half, right? Quite intuitive, I think. And what do you do with it? Do you give this picture or figure when you are writing the paper? No, you are not giving this. This is for yourself to evaluate if your results are reliable. So if your chains are mixing up, it's good. Then you can go further. So what is further? What is next? The next is we have to do, remember what is our goal, right? We want to do estimate our posterior distribution of our unknown parameter. So then our final goal or the end point of the analysis is to obtain the posterior distribution of the parameter. So then what is the posterior distribution? It is this one. It is this one. And what is that? It is actually summarized by estimating the density over the 4,000 samples. So think with me. We have 4,000 samples. We can actually do, let me do this first. So those are the 4,000 samples, right? This is from 1,000 to 2,000, but we have 4 chains. In total, we have 4,000. So imagine what we did from previous lecture. So we have a sampler. It starts, can you see this? Maybe other color, green. Yeah, kind of. Okay, so you start from here. You visit. Okay, you do this visit until you turn to the end. So what you can do is you summarize how often you are visiting this place, how often you are visiting this place, how often you are visiting this place. So you just summarize the frequency. And then what you eventually get is, well, maybe this location, you visited that many of times, like bar or histogram. This location, you visited that number of times. And here, this location, you visited only maybe twice. You don't visit there often. And here, this place, you don't visit there very often, also very low. And then here, maybe some number you are visiting here. And then here, some number you are visiting here, okay? So eventually, you will have a histogram of all of the visits. And because the visits is a discrete variable, you want something to be continuous. So there are approaches to estimate a density from those visits, okay? So those are then our results. If you see what's coming next is actually the density. The density is estimated directly from the samples. So when we are doing Bayesian analysis, as long as we have the MCMC samples at hand, we can literally do anything. We can estimate the density, we can split, now I can explain this, we can split the chains, right? We have, this is the summarize the results of all of the 4 chains taking all together. But let's say if I'm interested in the estimation of chain 1, chain 2 separately, I can also do that. And then taking all together, it is the left one. And also to recall that earlier we did a grid approximation in R, like using the sequence function to generate a few equal-stepped grids to do the estimation, like doing an analytical approach of the binomial model. We have this one. So if you look at the shape, they're pretty much the same. They are pretty much the same. It should be, because they are using different 2 approaches to solve the same problem. And then we can draw a conclusion to really finalize this part. So we have, let me start from the beginning. So this beginning is the beginning of this example. So we have a research question that we are interested in how much water is covering the entire Earth. So what do? We do experiments to test our hypothesis or to examine our research question. So we have a globe and we told we catch water, land, water, land. We have 9 times of experiment, and out of the 9, 6 times are water. We are interested, we are hypothesizing that there is a proportion of water covering the land, which is unknown parameter theta. And we constructed a model, which is a binomial model, to quantify this process. And then we estimated this parameter, the posterior distribution. Using Bayesian approach, we estimated the posterior distribution of this parameter. Here, same thing. And instead of only a point estimation, we are able to get an entire distribution of the parameter, which is actually the uncertainty. And I think I mentioned earlier that if we have 900 and 600 here, the peak will be pretty much the same, but the width of the distribution, the shape of the distribution, it will be different. It will be much narrower. In other words, it will be less uncertain. It will be more precise, right? So then the relative plausibility of here, this is the highest, but it never rules out the possibility that theta being other values. So if we have theta equals 0.5 or theta equals 75, can we also observe this result? Yes, we are able to observe it, but it is less plausible than this number, okay? So in the end, we have a whole range of thetas, all of the theta. From 0, let's say this. We have water, land, 9 times. We have 0 to 1 parameter. So all of the parameters, all of them, maybe excluding 0 itself, maybe excluding 1 itself, all of the parameter space, the continuous space in between 0 and 1, we are able to observe this sequence. Just that some of them, they are more likely, some of them, they are less likely. And then the distribution quantifies this uncertainty, okay? Good. Yeah. And this question we covered. So do we need the uniform? No, if we are using uniform distribution, we don't have to do it. But if we are trying to, if we are indeed interested in some other shapes of prior distribution, then we do have to specify the prior distribution in the model block. Okay, good. So then what I can do now here is, well, I showed you the figures on the slides, but how do you actually generate those figures? It turns out that in the STEM package, there are very nice plotting or visualizing functions that we could use to visualize our posteriors. So this is the fitting object that we obtained from this function, right? As usual, if we are using some new package and we don't know what is the data type of this variable, what we do. So it is called data globe. Of course, we say class of it, right? Because this is a new thing. So what do we have? This is a special class. We've never seen it before. It's never there in the original, in the in the base R. So this is a new data type that belongs to this package, okay? So when this is a stand fit object, we can do multiple things. So here printing is one of them. We are able to print the table that we saw. And we could also plot it. So here in this case, I say, well, I want to, did I? No, stand trace, it's not there. Load it. Yeah. So if I plot the trace, so what is trace? This is trace. This is the chance. This is the traces of all of the MC visits. I can do two versions. I can either include the first half or not. So here it means I don't want to include the first half, equals false. I include the warm, no, false. But if I do want to include it, yes, I could do it. Then I just simply turn on that flag. So that's, can you see here? Not yet. Here, there's a shaded area in the first half. These are the warming up period. And we are interested in the final posterior distributions. Then this is the one. So what is function? It's called stand dense. It's for density, okay? And this here means, do I want to plot all the chains all at the same time, like irrespective of the chain ID, or I plot the densities per chain separately. In this case, it is in this way. Those are the useful functions that you might encounter or need in the future. Questions here? Good? Oh, good. Okay. And what I want to do the next is to spend a few seconds on explaining the Stan language a little bit more. So we had one binomial example, and I showed you how to code it from bottom up, but there are structures, there are grammars to look at. Like if when we are learning a language, there is a noun first, subjects, and then there is a verb, and then there's something like later. We have to follow these rules, right? What are the rules of the Stan language? There are also the rules of the Stan language. But first of all, and if you heard about JAX or BAX, those are the earlier version of the MCMC sampling methods. So they take time, they're less efficient, they take also more memory, and they are not so much nicer language features. I just quickly mentioned this. So all in all, I just want to say that, well, if you are learning Bayesian statistics, if you wonder which language you want to start with, you just start with Stan, right? Okay, good. And this is quite a kind of a comparison of the performance of different languages. So this is the actual parameter space. It is not actually two-dimensional. It is two-dimensional of a highly correlated, in total 250-dimensional space. And we are taking the marginal two-dimensional irrespective of the others. So eventually, if, let's say I can try to draw. So if the algorithm is efficient enough to sample the entire parameter space, it will just travel everywhere, right? It will just travel everywhere to sample from this true parameter space. This is truth. But it turns out that this method is stuck in everything in between. This also stacks. So for some reason, first half of the truth. But this is the one that is used in Stan. So HMC uses a specific sampler called NUTS. So no U-turn sampler. You see here, it travels the entire parameter space, and these two are more or less equivalent. So now we are basically showing that Stan is efficient, it is reliable, and it is better than the others. And also look at here. So these two approaches, they are also using a super long chain, right? Instead of 1,000 or 2,000, it is 1,000,000 proof, but just 1 million. It is 1 million samples of the MCMC chains, also thin to be 1,000. It takes every 1,000 sample of it with the aim to get rid of the spatial correlation, but it actually didn't help much, right? If you see here, this is still quite stuck within the area. But anyway, Stan is good and we use it. This is the message I want to convey. It's quite straightforward. All right, so what are the language features? And we know that white space doesn't matter, I showed you, and comments double slash, and every single line must be terminated by semicolon. We also know that now. This is important. So all of the variables are typed and scoped. So what does that mean? So typed here means we just have to declare all of the data types of the variable. So scope, I will skip this for now, and I will tell you later. So typed, this means everything has to have a type. Skip these lines, doesn't matter. So if it is a real number, I will have to say this is a real continuous, right? Then conversely, if it is a integer or discrete variable, we say integer. But oh yeah, okay, something additional. So we could also provide the lower boundary and the upper boundary using this smaller, larger sign and triangular parentheses. Those are the limits, the ranges. And we don't usually deal with only one single number. It's either real or integer. It's just one number. But what we have a larger data set. We have maybe a vector. We have also maybe a matrix. So how do we do that? Here we have the dedicated data type called vector, and the dedicated data type called row vector and matrix. So the difference between vector and row vector is, by default, vector is a column vector. column vector. So column vector is this. If it is a column vector of 3 elements, it has 1, 2, 3 elements. Conversely, if it is a row vector with 4 elements, then we have something like this. Okay, 1, 2, 3, 4. Just the direction or orientation, vertical or horizontal. The matrix is easy, I guess. So the first dimension is the number of rows. The second dimension is the number of columns. So in this case, we have 3 rows and 4 columns. Okay, like this. And in total, we have 12 elements. So let's say we have capital A. Capital A is this. And one interesting thing is if we say, well, I have the first one, this is index. We have A1, the A of 1. What is A of 1? The A of 1 is actually here. This is A of 1. This is A of 2. This is A of 3, okay? And instead, there's, I don't know, maybe there are some new developments, but a few years back, there is no way you can do this to say, well, I want the first column, and this is not there. If you do want to have the first column, there is a function, I think it's called call to get the column of A, and then I want the first. This is possible, but this way of index, I'm not sure anymore, but back then it's not possible. It was not possible. The question here is perhaps why you need it, right? Why you need to have a subset of rows or subset of columns, because it depends on the model. Occasionally you need to go back to a few more. This is not a good example. Let's say that you have a memory example. You have a memory exercise, a memory task. Let's say the most recent one you are remembering very well, and then the second to the most recent one you are still remembering, but a little bit vague. And then the 1/3 back, or 4th back, and 5th and 7th back, you don't have a quite good memory. This is called decay, right? This is called decay. Let's say this is trial, this is number T, and we have a memory tree somehow like this. So this is the most current one you remember very well, and then as long as you're going back into the history, you don't remember, you forget. So then we have this kind of data. We want to go from, let's say, we have the data. This is not good. We have data, and let's say I'm now at trial T. I want to go from the first to the Tth, okay, of the data. And the data will be the input for building the model. So this is a place where you might need to index your data matrix. Good. And then here we say, well, can we also give the lower and the upper boundary of a vector? Yes. For a row vector, yes. Matrix, yes. Just do this slower and larger, smaller than the larger than sign, and then you just give the lower and the upper boundary as we did for scalars. Good. And something else. So if we are doing a model and we quite imaginably, we will also have some if-else statement and for loop. So let's say if your reaction time is less than 400 milliseconds, do something. And if the reaction time is larger than 400 milliseconds, do something else, right? If else. The good news is that the if-else statement and also the for loop, looping from first person participant to the last participants, and then inside looping from the first trial to the last trial, this for loop, the good news is that the if-else statement and the for loop instead is the same as R. The only exception is that we have to enter the semicolon per line. So if, let's say, this is R, then this is stan. Okay, it's only difference. We need semicolon. Other than that, it's the same. This is good news because we don't have to learn a new way to specify the if-else statement, to specify the for loop. Okay, questions at a moment. Okay, all good. Okay, then I'm going here. So I said, well, the variables are typed and scoped. I explained the type. You have to give a type to the variable. You have to specify it. What is scope? What does scope mean? So scope means where do I know it? So this is not a good example. Scope means the scale, how large one variable is known to the entire. Also not a good idea. How can I know that? How can I give one example? Okay, this might be a good example. So we have a supermarket called Billa, right? It is known to the local Austrian market, but maybe it's not known to France. So then Billa, the market, is a local brand. It is not a global brand. And instead, there's something called Siemens. We know there's some like dishwasher, fridge, and also our MRI scanning. They are from Siemens. Every person knows it. So this is a global brand. So just local and global, right? So how much this is known within the environment. For this programming language, it has the same thing. So if I declare the data, so we have 6 blocks, right? We have the data block, transform the data block, parameters, transform the parameters model, and generated quantities block. Those are the blocks. Imagine those are the countries in Europe. If I declare a data, it means everywhere we also know the data. So if I say n equals 9, 6, w equals n equals 9, w equals 6, then every block in our model file, they have to know that those are the data. Okay, so the data thing, if anything you declare data is like the global brands, Apple, Microsoft, Siemens, something like this. And it turns out that all of the 4 blocks, everything you define, they are global. But what you declare, only declare in the model block, they are local. Okay, they are like if you just go to Austrian Billa market and nobody else knows it. This is fine. So as long as you are within the same region, you are safe. You know where to go. You know what you can get. And here the generated quantity is the same. This is also local. Okay, this is global and local. This is quite important, I think. And all the others is a little bit too much. I don't want to explain. But this global and local thing, this is quite important. Okay, maybe too much for you. Questions? Oops. Good. Let's do some exercise. So we know that either we have a globe tossing, we have a coin tossing, we have the exam, we have the penalty shootouts. They have binary outcomes, yes, no, and 0, 1. So let's maybe program one of a special case of the coin tossing example. So which follows a Bernoulli process or Bernoulli model. So what is Bernoulli? Let's say in another case, well, we are interested in the research question about whether the coin is biased. So what can we do? We do experiments. We throw the coin and then catch it, and then to see which one is facing up, either the head or the tail. So then let's say we have head is H, tail is T, or 0, 1. Let's say we observed 15 heads out of 20 experiments, okay? And then let's say similar to what we assume that there is a theta% of water covering the land. Here we assume theta probability, the coin is biased towards the head, okay? So this is the same example. We could actually model the same thing using the binomial function. But let's say if I'm interested in this every single step, if let's say I only do one experiment, I have either head or tail. So this capital N becomes 1, and then the entire equation is simplified. It becomes like this. So the capital N is reduced. You don't have it anymore because it's equals N. This special case is Bernoulli model. Okay, so the Bernoulli model is a special case of the binomial. So when capital N equals 1, we have Bernoulli. When capital N is larger than 1, we have binomial. So as the earlier example of the globe tossing, we could graphically illustrate our model. So each single time, N is N, right? We have multiple single times, and each single time we have only one true process, the theta, and the observation, head or tail, okay? This is head, the theta follows. The theta means the proportion of the coin is biased towards the head. Good. So now what I want you to do is, actually, we have 15 minutes, I think is enough. So we could use something in Zoom called a breakout room. So I will just randomly assign all of you to small groups, 2 people, like you will be in your room. And the exercise is actually there. So if I show you close this. If you look at the folder, you have it. There's a folder called coin. And if you look at it, yeah, if you look at it, there is already kind of the model file, right? What I actually want you to do is don't open this. You open the R Studio shortcut. And then when you have it, okay, come on. Yeah. So when you have it, you create a new script and then save it as we did. So we say Bernoulli, well, my Bernoulli underscore dot stem. Yeah, just save a new stem file. And then let's say, well, I want to have data. I want to have parameters. I want to have model, okay? So since that you will be assigned to small groups, you will have multiple people. And then what you can do is you just write down your model and then try to fit it. Well, you don't even have to fit it. Just try to write the STEM model, okay? It's maybe a little bit challenging, but try it. It will worth it. Make sense? Okay, I guess you're ready for that. Somebody already left. Okay.